Hey guys, this is just a log summary from the sheet that I handed out today. Okay, so remember that logarithms are the inverse functions of exponential functions. So if we took an exponential function like this and we found its inverse function, which would be x equals 2 to the power y, and then we just rewrote that in log form, that's what it would look like. So just to show you what it would look like as an inverse function. We also talked about transitioning from logarithmic form to exponential form. So if you had a log base 3 of 9 equals 2 and you wanted to switch that into exponential form, you could rewrite that as 3 to the power of 2 is equal to 9. So the base of the logarithm is also the base of the exponential function. The argument of the logarithm becomes the answer to the exponential equation. And then the exponent of the exponential form is the answer in the log. And we can also go backwards. So if we have 4 to the power of x equals 16, we could rewrite that in log form as log base 4 of 16 equal to x. So that's how you can go back and forth between log and exponential, and you definitely want to know that. We learned a change of base formula, which is really helpful when we have a log that we can't evaluate. So if we had something like log base 2 of 10, well, we don't know 2 to the power of what equals 10, we don't know. So we could use a change of base formula in order to evaluate that. So we could change into log base 10 divided by log base 2. And you can change it to any base, but we would likely pick a base 10 because then our calculator can evaluate it. Okay, laws of logs. These are the 3 laws of logs that we learned. We learned the addition one, the subtraction one, the product, the quotient, and the power law. We learned how to evaluate logs. So if you have a log base 2 of 32, you're kind of thinking about, okay, 2 to the power of what equals 32? So 2 to the power of 5. So this must be equal to 5. If you have log 16 divided by log 4, you could rewrite that as a single logarithm by writing it as log base 4 of 16. And then if you wanted to evaluate it, you know that 4 to the power of 2 is equal to 16, so this would just be equal to 2. You can use logs of logs to help you evaluate logs. So if we have log base 6 of 8 plus log base 6 of 27, well, 6 to the power of nothing that I know equals 8. It's going to be some kind of decimal. So maybe using a law of logs will help us. So since I have an addition here, I know I can use my product law. So I know I can do 8 times 27. And then 8 times 27 is 216. And then I know that 6 to the power of 3 is equal to 216. So that would just equal 3. In this one, I can raise my logs to the exponent of 2. So I can make this one 2 to the power of 2. And I can make this one 5 to the power of 2. And then I could use my product law again and multiply them together. So 2 to the power of 2 would be 4 times 5 to the power of 2 would be 25. So then log of 4 times 25, which would be log of 100. And I know since I have a base 10, 10 to the power of 2 would be equal to 100. So the answer to that is 2. Simplifying logs. So I can use laws of logs, and I want to rewrite this using 1 logarithm, not 2 logarithms. So I'm going to write, since this is a subtraction question, I'm going to write these as a quotient. So I'm going to have 2m plus 6 divided by m squared minus 9. And then you always want to make sure the argument, this part is called the argument, you want to make sure that is simplified fully as well. So in order to do that, I'm going to factor it. So I'm going to say I can factor it to 2 to make it m plus 3. And then the bottom is a difference of squares. So I can say m plus 3, m minus 3. And then I can see that my m plus 3's can cancel out. So I end up with log 2 over m minus 3 as my simplified version. Here it says write as a sum or difference. So I'm kind of splitting this up. So these are currently being multiplied together. So I know using my law of logs, I can write this as a squared plus log b plus log c. And if I wanted to, I could even simplify log a squared to become 2 log a plus log b plus log c. And they're all multiplied together. They're all added because these are all being multiplied. Okay, the next part is all about solving exponential equations. And there's like 6 questions of these. These are probably even more popular than logarithmic equations. But we are going to use logs to help us solve them a lot of the times. So when we're solving an exponential equation, it'd be really great if we can make the bases the same. That would make these much easier to solve. So if I could somehow make them the same base, so I can see that 27 could be rewritten as 3 to the power of 3. And then I'll just keep that x minus 1 in brackets. So now that I've made the bases the same, it should be true that if you have 2 to the power of something, like let's say 4, and then you had 2 to the power of something else, it couldn't be something different, or else they wouldn't be equal to each other. So it must be something that's the same. So if your bases are the same, then your exponents must be equal to each other. So for this question, I can ignore my bases, and now I can just set my exponents equal to each other. I just expanded that bracket. And then I can just solve it like a linear equation. So I can subtract 3x from both sides, making it 2x equals negative 3. Then I can divide both sides by 2, making it negative 3 over 2 as my answer. Okay, this next question, you can see I have a 3 and a 5. Now that isn't going to be possible to make the same base. So in this case, I'm going to take the log of both sides of my equation. And I'm doing that so that I'm going to be able to get the x out of the exponent. So I took the log of both sides, and now I can use the power rule to bring down the exponents in front of the log. So now I'm going to have x minus 2 out front, log 3 equals x log 5. Now this x minus 2 log 3, I can distribute. I can make it x times log 3 minus 2 times log 3 equals x log 5. Now I want to get all of my x's, all my x terms on one side. So I'm going to say x log 3 minus x log 5 is equal to, and I'm going to move my negative 2 log 3 over to make it positive 2 log 3. Now I'm going to factor out the x to make it log 3 minus log 5 equals 2 log 3. And now I can divide both sides by log 3 minus log 5, making it 2 log 3 divided by log 3 minus log 5. And I know some people rewrote this as, which is also right, 2 log 3 over log 3 over 5 using the quotient law. So you can totally do that. You can also get a decimal answer if you want to. Maybe I should do that just so you can check your work. Oh, I'm just going to do that right now because I didn't do it yet. So 2 times log 3 divided by log, 3 over 5. So I got negative 4.3. I don't know if that's right. I'm just going to try it one more time. Sorry. 2 log 3. Okay, sorry. I'm not. 2 times log 3 divided by log 3 minus log 5 Yeah, okay, that's right. Sorry, delay in the video there. But anyways, moving on. Okay, this next question. 3 to the power of x equals 12. Well, I have an x in my exponent. I'm not able to make them have the same base, unfortunately. Like 3 and 12, I can't make that have the same base. So instead, I'm going to rewrite this in log form. You could also take the log of both sides. That would also work. But I'm just going to go right to logarithmic form. So I'm just going to rewrite this as log base 3 of 12 equal to x. It would also work if you did it the same as this question, where you take the log of both sides. That would work too. And then I'm going to use the change of base formula to solve this. I'm going to say log 12 divided by log 3 is equal to x. And then you can divide that using your calculator. But I'm not going to. You can also just leave it. Okay, next question. You have 10 equals 2 times 4 to the power of x plus 2. I'm going to straight off the bat divide both sides by 2. That's fine to do because these 2's can just cancel out. So that becomes 5 equals 4 to the power of x plus 2. Now I'm kind of in a similar boat to like this red one and this blue one, where 5 and 4, I can't make them have the same base. So I'm going to switch this to exponential form. I'm sorry, logarithmic form. And you could take the log of both sides, also works. Or you could switch it into log form by going log base 4 of 5 is equal to x plus 2. So then you know x is equal to log base 4 of 5 minus 2, which would be equal to log base 5 divided by log base 4 minus 2. And you could leave it like that. I'll just get that answer for you if I can. Log 5 divided by log 4 minus 2. So I got x is equal to negative 0.84, I guess. All right, moving on. 2 more exponential equations. So you can notice these are very similar, but things to note is this has an x plus 3 and this guy has a 2x. So you're going to solve them very differently. In this one on the left, I am able to factor out a 2 to the power of x. So when I factor out a 2 to the power of x, it's like I'm dividing each term by 2 to the power of x. So when I divide the first term by 2 to the power of x, I get 2 to the power of 3 left over. Which might seem weird, but if you think about like exponent laws, 2 to the power of x times 2 to the power of 3, when we multiply things with the same base, we add their exponents together. So we can see that 2 to the power of x times 2 to the power of 3 would actually be equal to 2 to the power of x plus 3. So that checks out. Plus, then we have to divide it by 2 to the power of x. So that would just be 1 equals 36. So this helps us a lot because 2 to the power of 3 plus 1 is definitely solvable. So 2 to the power of 3 is 8 plus 1 is 9 equals 36. Then I'm able to just divide both sides by 9, getting 2 to the power of x equals 4. And then I know 2 to the power of 2 would be equal to 4, so x must be 2. So it's not bad. The next one, however, is slightly different. We're not able to factor out a 4 to the x or a 4 to the 2x. That's not possible. So what we have to do is we have to let a variable, let's say n, represent 4 to the power of x. Because this actually is a factorable equation, we just can't see it clearly. So if we let n represent 4 to the x, we can rewrite this as n squared, because 4 to the power of x is now n. So we just have n squared, minus 4 to the power of x, so that's just n, minus 20 equals 0. So often you'll have to let variables represent kind of like other things just to make it easier to see the solution. So then we can factor this. So two numbers that multiply to negative 20 and add to 1 would be negative 5 and positive 4. And then we can say that n minus 5 is equal to 0, so n must be equal to 5. N plus 4 is equal to 0, so n must be equal to negative 4. And then we can replace n with 4 to the power of x. 4 to the power of x. And then we can solve for x. So in this case, 4 to the power of x equals 5. I cannot tell what x equals. So I'm going to swap that into logarithmic form. So I'm going to say log base 4 of 5 is equal to x. And then I'm going to use a change of base formula. So log 5 divided by log 4 is equal to x. So that's one solution. This one, 4 to the power of x equals negative 4, that's not possible. So if I switch that into log form, log base 4 of negative 4 equals x. If you try to evaluate a negative argument there, like a log negative 4 divided by log 4, you cannot. So, and that makes sense, right? Because 4 to the power of nothing is going to give you negative 4. So you can't do it. It's inadmissible or erroneous. So you can just leave that out. So that would be our only answer. So that's not possible. Okay, that's our exponential ones. And here are our logarithmic equations. There's 3 of these. So for the most part, you're probably swapping it into exponential form. So I've got the variables in my argument. I can't really get it out of there. So instead, I'm going to switch this to exponential form. So I see I have a base of 10. My exponent is a 2. And it's going to be equal to the argument 2x plus 10. And I just solve this. So 10 squared is 100. Move my 10 over, so I got 90. Divide by 2, so the answer is 45. Next question. This one, before I can do anything, I'm going to use laws of logs to simplify it. So it's going to become x over x minus 2 equals 1. So now it's kind of like the first one. I just needed to do a little bit of work to get it like that. Now I can swap it into exponential form. So 5 to the power of 1 equals x divided by x minus 2. So 5 to the power of 1 is just 5. And then to solve this, kind of like a rational expression, I'm going to multiply both sides by x minus 2. So then these guys cancel out. And I'm left with 5x minus 10, if I expand that out, is equal to just x. Now I want to get my x's on one side, so I'll say 4x is equal to 10. Divide both sides by 4, so I get 10 over 4, which I could simplify to 5 over 2, and I always should simplify to lowest terms. And the final question here, I'm going to use laws of logs again. So log base 2 of x times x plus 2 equals 3. Now I can rewrite this in logarithmic form, so I just had to do a bit of work to get it like that. Now I can rewrite it as 2 to the power of 3 is equal to, I'm just going to expand this to make it x squared plus 2x. And I'm going to bring my 2 to the power of 3 over. So I know 2 to the power of 3 is actually 8, so it becomes minus 8. Then I'm going to factor it. So I want to like two things that multiply to negative 8 and add to 2. So I'm going to go with 4 and negative 2. Then I'm going to solve for x. So x must be equal to negative 4, or x is equal to 2. And I can see that negative 4 is not going to work. So all I do to check is I go back to my original logs and I just try, like, what if I put log base 2 of negative 4 in? We can't solve that. We can't have a negative argument. The other one's going to be negative as well, because negative 4 plus 2 would be negative 2. So they're not, this is not a solution. It's called an erroneous root, or you can say inadmissible. This is our only solution. Okay, then finally the graphing. So graphing transformations, so we've got these transformations A, K, D, and C. So you should be able to describe how they're affecting the graph. So in this case, we have a K value, and that's going to be a horizontal, in this case, it's going to be a stretch by a factor of 2. K always affects your transformations by a factor of 1 over K. So 1 over a half would be 2. And it's going to shift your graph up 3. So there's two transformations happening to this graph. My personal preference for graphing is to use 3 key features. So the first thing I like to do is find the vertical asymptote. And I like to do that by setting the argument equal to 0. So my argument is 1/2, that's the argument. And I'm going to set that equal to 0, and then I'm going to solve for x. So if I divide both sides by 1/2, I just get 0. So I have a vertical asymptote at 0. So I'm just going to graph this as I go. So I know my vertical asymptote is going to be right at x equals 0. Then I'm going to find 2 points, and I'm going to pick really clever points. So I'm going to actually set my argument equal to 1 every time, because then I just know I'm going to have a nice value to work with. So I'm going to set my argument equal to 1, and then I'm going to see what does x equal and what does y equal. So if I set it equal to 1, x would be equal to 2, because I just multiplied both sides by 2 to isolate x. And then I have to find y. So I go back to my original equation, log base 2, 1/2 times 2 plus 3. Y equals log base 2, 1/2 times 2 is just 1, which is what we made it, plus 3. Then log base 2 of 1 is 0. And then 0 plus 3 is 3. So now I know I have a point at 2, 3. So I can plot that on my graph. So at x equals 2 and y equals 3, I'm going to have a point there. And then I'm going to find one more point. I'm going to set the argument, 1/2 x, equal to whatever the base of my logarithm is. So the base of my logarithm is a 2. So I'm going to set that equal to 2. And then I'm going to solve for x. I'm going to times 2. I'm going to multiply both sides by 2 just to get rid of this fraction. So I get x must equal 4. And now I need to find my y value. So log base 2, 1/2 times 4 plus 3. And I'm going to solve it. Log base 2, 1/2 times 4 is just 2 plus 3. Log base 2 of 2 is just 1. And then 1 plus 3 is 4. So I'm going to have a point at 4, 4. There. So I can see that my graph is going away from my asymptote. So that means this side must be approaching my asymptote. If you wanted to find your x-intercept, you could sub in 0 for y and then solve. You could do that to get a more accurate x-intercept, up to you. But that'll work every time. All right, that's it. That's the whole course, the whole unit.